Now, I said that in calculus we're looking at
Underfield.
rates of changes and how things change into another thing. So this graph over here, it's meant to represent when you're driving a car. And when you want to find the gradient of the line, generally how have you done that? How have you found the gradient previously? What do you need? Rise and run, yeah? So you need 2 points. And here I've got 2 clear points. I've got the point,
That and
5,
distance and time.
400. And here I've got another point here, 0, 0. So that's 2 points. So if I look at the rise over the run, I can find that really easily. All I have to do is find 400 minus 0. That's the rise. And the run, well, that's how far I go across. That's just 5 minus 0. That gives me 400 over 5.
So you couldn't use 20.
Yeah, but it depends where you start. Yeah. So you can see that this gradient has actually found something for us. What has it actually found?
The kilometers per hour.
Yeah, right. And it's found the rate, right? The speed at which I'm going at. So this gradient is an important idea at finding things in certain scenarios. And we're going to see that come into play a bit later. But let me just bring your attention to this. This is actually Usain Bolt's distance versus time graph for his world record in Berlin. I can't remember when it was.
Yeah, it was Berlin.
Berlin? Right.
2011.
2011?
Yeah, 2011.
It was 9.58 seconds, okay? So the first question I asked you was, find the average speed, right? And that's really easy to find. All you have to do is distance over time. What did you have for that? So speed equals to the distance he covered. So that should be 100, right? 100 meters. And what was the time that he took? He took 9.58. Okay.
He showboats at the end. So it's going to go a little
No,
down.
Nick, he's faster.
What did you get for that? Was it 10.4?
10.4.
What's that actually representing? This is actually...
Miles.
Yeah, right. Meters per second, right? It's representing the meters.
Runs at 10 meters a second.
He runs meters a second.
That's on average. So like,
Right. Okay, that's the important part. Because the second question... What's the second question, Cal?
Find the speed at 8 seconds.
Find the speed at 8 seconds.
How would I do that?
Can you
80
over 10?
80 over 8.
80 over 8, sorry.
So you're saying...
you just look
In
at
yeah, right. So you're saying at after he's done 80 meters,
Yeah, you got over 8.
it's taken him 8 seconds.
Yeah.
So you say, okay, let's just do distance over time again.
10 meters a second.
Can anyone see?
That'd be the average still though.
Right. Can you see the problem with trying to do that? What you're actually doing is you're saying that over this period of time,
The average.
he's traveled 80 meters and it took him 8 seconds.
Yeah.
So the average speed is still what you're finding.
10 meters.
Oh, yeah,
Within
you
the
can't
last
grade it.
20 meters, he's like, it's a minute.
Yeah.
And the important thing is to know is that this graph is curved, right? His speed is constantly changing. It's not like he's running 10 meters every second, each second.
Well, the
That's
start's
just
obviously
that's just an
reaction time.
average, right?
Crazy.
That's
You got
just an
reaction
average.
time at the start. Like the other
Exactly.
one.
There's other factors in there. But the important thing I want you to understand is we can't simply find the speed at a certain point very easily. You actually have seen speed at a certain point exactly every day. I don't know if you realize.
In the car.
Right, in the car. When you look at a speedometer in your car, it's saying at that exact moment you're traveling 60 kilometers per hour. But you just found out that it's actually really tricky to think about how can you even find out if what you're traveling at a certain time. I'll give you an example. Say you're driving along a road.
Instantaneous speed.
Right, say you're driving along a road and you want to find instantaneous speed, so the speed right this second. And say you say, okay, there's a stop sign up there. Oh, not a stop sign, that's a bad example. Let's say you don't want to pass through the stop sign. Let's say there's a let's say like that's a bad one.
School zone, speed up more.
Let's say there's like a wombat sign.
Means a lot. Wombat sign.
Okay.
Fair enough.
So we're driving up to it and we say, okay, to find the instantaneous speed, I already know. Coming back to 11. Coming back. Jesse. I already realized that the formula for the speed is the distance over time. Okay. So say I want to find instantaneous speed. So I'm saying, okay, when I get to this sign, I'm going to count the amount of distance I cover and the amount of time it takes to do that. Can anyone see a problem with that?
You have to count through things at once.
It's still average.
And
it's
it's the
still not
average.
the
You could be
instant
going
time.
quicker or slower.
It's a time over. It's a speed
You know,
over a
yeah,
certain
like-
amount of time.
Well, let's say I'm at the sign. I'm saying, okay, I'm going to count how long it took and how much distance I covered.
To where?
Well, exactly, that's the problem, right? To where, right? If I can't really find it because it's the same location, it would actually be 0 over 0, right? I would have covered, if I'm at the sign, I haven't covered any distance, and yeah, that's true. I haven't covered any distance, and it took me 0 seconds, because I'm just at the sign, okay? And that's the problem that Newton and Leibniz encountered. They couldn't find, using their current knowledge of mathematics, how to actually calculate something like this. And the gradient we're going to find is going to become really important in doing this. Just as a little backstory, how this actually originated was Newton was trying to understand, this is one of the stories, Newton was trying to understand why the planets orbit the way they do around the sun. Does anyone know what shape they orbit in?
It's like it comes and then it comes in skinnier than you.
There's a name for it.
Oval.
No, it's.
Yeah, it's elliptical, right? So someone was asking Newton, why do the planets orbit the sun in this way?
Gravitational.
He didn't have an answer for that. He said, "I'll get back to you." And so he was thinking, and he was looking at his current form of mathematics. He couldn't find anything that would help him answer that question. So he invented his own field of mathematics to do that. And he came back and he realized that these ellipses, they're actually a part of a cone. They can be looked at cross sections of a cone, and that's how we can understand the orbiting shape of the planets. And then he turned 26. So he did a lot of things in his life. And that's what we're going to look at. This is the whole field of calculus we're going to look at. We're going to look at how can we find the instantaneous rate of change. Okay? Can you get this down?